Hello everyone. Myself Manjusha Sanap, Assistant Professor, Department of Pharmaceutical Chemistry from Shivajirao Zondale College of Pharmacy, Asangaon. Today's topic for my lecture is U-visible spectroscopy, its principle and application. Spectroscopy. Spectroscopy is the branch of science that deals the study of interaction of electromagnetic radiation with matter. Spectroscopy is the powerful tool available for the study of atomic and molecular structure and is used in the analysis of wide range of samples. It is of mainly two types. Spectroscopy, it is of mainly two types: atomic spectroscopy and molecular spectroscopy. Atomic spectroscopy is concerned with the interaction of electromagnetic radiation with atoms are commonly in the lowest energy state called as a ground state. And molecular spectroscopy, this spectroscopy is dealt with the interaction of electromagnetic radiation with the molecule. So what is electromagnetic radiation? Electromagnetic radiation, it consists of discrete packages of energy which is called as a photons. A photon consists of oscillating electric field and magnetic field, and these two fields, electric field and magnetic field, these two fields are perpendicular to each other. So these are the properties of electromagnetic radiation, that is the light. So we already discussed spectroscopy means it is a method of analysis based on interaction, absorption or production of light by matter. That is the interaction of electromagnetic radiation with the matter. Light is considered as a electromagnetic radiation. There are two forms of light. One is particulate form and one is wave model. So this is the wave model, means the electromagnetic radiation, they are available in wave model. So what is wave model? It is represented by sinusoidal wave traveling in space with oscillating electric field and perpendicular magnetic field. So it is given or it is shown by in the diagram. There is a oscillating electric and magnetic field and both fields are perpendicular to each other. So this wave, it consists of amplitude. Amplitude means it is the height of waves and it is the electric vector. Then wavelength. Wavelength is given by the lambda. It is given by the symbol lambda. It is the distance which measure in nanometer, centimeter, meter from peak to peak. Means it is the distance between one crest to other crest of that wave or one trough to other trough of that wave. So it is called as a wavelength. And wave number. Wave number, it is inversely proportional to the wavelength. It is inversely proportional to the wavelength and therefore it is given as a centimeter inverse. Their unit is centimeter inverse. Then particle model of the electromagnetic radiation. We seen the wave model. Now particulate model of the wave. So light view as a discrete particle of energy, that is the photons. Like other particles, light can be scattered or counted. Like other particles, light can be scattered or counted. So when the light, when a molecule get the energy required of photon to give the transition from ground electronic state, that is E0, to they get excited to higher energy level, that is E1, and the energy absorbed or the energy required for that transition is delta E is equal to E1 minus E0. The energy of that wave or that particle is equal to E is equal to h mu. So mu, it is the frequency. lambda, or it is also written as a sc by lambda. So c, it is the velocity of light, and h, it is the Planck's constant. Energy is proportional to the frequency and wave number, and it is inversely proportional to the wavelength. This is the different these are the different electromagnetic radiations. So this is the electromagnetic spectrum. So these are the different electromagnetic radiation, that is the radio waves, microwaves, infrared radiations, visible radiations, UV visible radiation, uh, X-rays, gamma rays, and their energy. Then how this electromagnetic radiation interact with the matter? Electronic energy level. Every molecule at room temperature, they are at their lowest energy level. Every molecule, they undergo three form of energy: electronic energy, vibrational energy, and rotational energy. So electronic energy, so every molecule at room temperature, that molecule at their lowest energy level, that is the E0, that is the ground state energy level. When the molecule absorbs the UV visible light from the EMR, one of the outermost lone pair of electron is promoted to their higher energy. They get the energy and they promoted to higher energy level such as E1, E2, etc. is called as a electronic transition, and that their difference is measured as a delta E is equal to H mu is equal to En minus E0. So higher energy level is minus their ground state energy level. Then molecule also undergo vibrational energy level. These are less energy level than the electronic energy level. Means every electronic energy level, they possesses some different vibrational energy level. The spacing between the energy levels are relatively very small. It is 0.01 to 10 kilocalorie per mole. Example, when IR radiation is absorbed, molecules are excited from one vibrational level to another, or it vibrate with higher amplitude. So IR radiation is related to vibrational energy level of the molecule. Then rotational energy levels. These energy levels are quantized and discrete. The spacing between the energy levels are even smaller than the vibrational energy. So this is a very less energy level compared to vibrational and compared to electronic. So therefore it is mentioned here. Then now we can see the principle of UV visible spectroscopy, and for this principle we can learn the Lamberts law. Lamberts law: when a monochromatic radiation is passed through a solution, the decrease in the intensity of radiation with thickness of the solution is directly proportional to the intensity of incident light. Now let we consider I be the intensity of incident light, x be the thickness of the solution, and now the equation becomes: there is a decrease in the intensity of light with the thickness of the solution is directly proportional to the intensity of incident light. So therefore here we derive the equation minus di upon dx directly proportional to the I. Minus di upon dx, it explains the statement: there is a decrease in the intensity of radiation with the thickness of the solution, and that is directly proportional to the intensity of incident light. Now we integrate this equation between the limit I is equal to I0 at x is equal to 0 and I is equal to I at x equal to 1. So the integrated equation, integration I upon I0 is equal to minus KL. Now we convert this into a log terms, and finally we get minus k upon 2.303, or log of minus I0 upon I is equal to log of I0 upon I is equal to absorbance. K upon 2.303, it is the absorption coefficient, and therefore absorbance is equal to absorption coefficient into L, that is the path length. Beer's law. When a monochromatic radiation is passed through a solution, the decrease in the intensity of radiation with the thickness of solution is directly proportional to the intensity of incident light as well as concentration of the solution. So therefore we consider I, it is the intensity of the incident radiation, X be the thickness of the solution, and C be the concentration of that solution. Then the equation become minus di upon dx is directly proportional to C into I, and then we derive this equation, integrate this equation, and finally we get the equation A is equal to E into C into L. So E is equal to absorption or molar extension coefficient, C it is the concentration, and L it is the path length of that solution. The principle, the UV radiation regions extend from 10 nanometer to 400 nanometer.